All right, welcome. We're going to go ahead and talk about Lesson 2, Applications of Derivatives. In this lesson, we're going to be using the first and second derivatives to find velocity and acceleration given a position function. And we're going to try to determine when an object is at rest, speeding up, or slowing down, again, using those functions. Okay, so let me go ahead and talk about the scenario here. A ladybug moves along a branch so that its position from the trunk of the tree at time t is given by the following function, s of t. That function is good for t values between 0 and 5. S of t is measured in yards, and t is measured in minutes. So here I have a nice picture, I think, that can help us kind of understand what's going on here. So we start out, we have this ladybug that's on the branch, and the S of t, what we're measuring here is this distance that the ladybug is away from the tree trunk, right? So a position of 0 would represent it's all the way up there against the tree trunk, whereas a position of like 4 would mean that it's 4 yards away, right? Because yards are the units that we're dealing with. And then our time is being measured in minutes, right? So it's not happening super quickly because a ladybug doesn't, zip around, but it's kind of walking along the tree branch. All right, so we're going to find an equation for the velocity. Turns out that velocity is equal to the derivative of our position function, right? Our position function has units of yards, whereas when we talk about the derivative of that position function, we'd be talking about yards per minute, right? So that is going to be equal to our velocity. Yards per minute is a speed or a velocity here. So taking the derivative of that function, here we have our derivative of the first term is going to be 2t, and then the derivative of that second term is going to be minus 6. And then finally, the third term is just a constant there, so when we take the derivative of that, we just get 0. Okay. This velocity function will have the same restrictions as the original function, right? It's only going to be valid in that same range of t values between 0 and 5. All right, let's go ahead and go down here. Next, we're going to kind of sketch a graph of v of t. Here you can actually kind of see I've already done that on there, but I'll go ahead and talk about it. So our velocity function is a simple linear function, right? 2t minus 6. So 6 all the way down here is going to represent our y-intercept, negative 6. And then the slope is 2. So we're going up 2 units over 1, up 2 units over 1, up 2 units over 1, and so forth. And that creates this nice linear graph, which is our velocity. Next thing we want to do is we want to go ahead and use proper units to label these axes. So our x-axis or our t-axis is going to represent the minutes. So you can see here we've graphed from 0 to 5 over here. And then our y-axis or our v of t represents the velocity, which is in yards per minute. Right? That's the rate of change of our position function, right? Position function outputs yards, and its input unit is minutes, so we have yards per minute. All right. So again, going back to our illustration, kind of want to talk about this here really quickly again, because we're measuring this distance, right, between the ladybug and the tree trunk for our position. When that position is getting larger, right, when it's increasing, that means the ladybug is moving to the right. Whereas when the ladybug is moving closer to the tree trunk, that distance or that position function is going to be getting smaller, decreasing. Okay. What does a negative velocity tell you about the direction the ladybug is walking, right? A negative velocity means that our position is getting smaller, right? The position is going from maybe 4 yards to 3 to 2 to 1, right? It's decreasing, which means that the ladybug is walking towards the tree trunk. So towards the tree trunk. Whereas a positive velocity, that indicates that the distance is getting greater, right? It's going from maybe 2 yards to 3 yards to 4 yards. It's getting greater. That's a positive velocity. That ladybug is walking away from the tree trunk. And we can see on our graph here that we actually have both negative velocity that occurs in our interval between 0 and 5 here, right? These are all going to be negative velocity values, right? At 0 minutes, it's all the way down here at -6. At 1, it's down here, right? And then we also have positive velocity values up here, right? At 4 minutes, we have a +2 velocity, and so on. Okay. Question 3. At what time is the ladybug at rest, right? At rest means the ladybug's not moving. And we can see that this is going to occur right here, right? That's at t equals 3 minutes. How do we know that, or how do I know that? I know that the ladybug is at rest there because its velocity is 3. Velocity is 0, velocity is 0, right? This is 0 on the y-axis, which is representing our velocity. All right. In question 4, we're going to be examining what's happening with the ladybug at t equals 1. So we're going to look at 1 minute, what's happening. So first off, let's find v of 1. So v of 1, I'll go ahead and use our equation to represent that. So that's going to be 2 times 1 minus 6, right? 2t minus 6. Evaluating that, we get -4 yards per minute. So the ladybug is moving at a negative velocity, moving towards the tree trunk, -4 yards per minute. Find v prime of 1. Okay. So we're going to be figuring out the derivative of our v function here. Derivative of v is equal to 2, right? Because this is 2t. And when we take the derivative of a linear term like that, we just get that constant that's in front of it. And then the derivative of this term, 6, is just going to be 0. That's kind of interesting. The derivative of our velocity function is a constant like that. What does this answer mean in the context of this problem? It means that the ladybug has a constant change in velocity, or a constant acceleration. So this acceleration is 2 yards per minute squared, right? Or yards per minute per minute. Remember, if we go back to our previous lesson, the units of this derivative are going to be the units of v of t over the units of t, so yards per minute, or yards per minute squared. So this is telling us that throughout the entire time, the velocity is always changing at this particular rate the whole time. All right, at t equals 1 is the ladybug speeding up or slowing down. Now this can be very tricky because speeding up is kind of a confusing term. We think of speeding up as just getting a bigger number, right? But velocity has a direction component to it, right? Velocity, we can be moving in the positive direction or moving in the negative direction. And so speeding up could mean I'm going faster but in the negative direction, or faster but in the positive direction. So you have to be really careful here. And so we know that at 1 second, our velocity is -4 yards per minute. And we know that our acceleration, I'm just going to go ahead and call this our acceleration A of 1, is 2 yards per minute squared. So because these two things are acting against one another, one of them is a negative value and one of them is a positive value, what's happening is even though we are going at a negative velocity, we are moving towards the positive direction, right? That velocity is actually increasing, which is going to be moving it towards the positive numbers, which actually means that the ladybug is slowing down. Ladybug is slowing down. All right, last question here. Off on another branch of the tree, a worm is crawling at this velocity. -4t plus 3. Where v of t is measured in yards per minute and t is in minutes. So that's the same units that we were dealing with before, right? Yards per minute and minute. Find a possible function that would give the position s of t. Okay, so this is a little weird. We are not calculating a derivative here, right? Because going from velocity to position is not a derivative. Going from position to velocity, that's the derivative. So we're actually doing something called an antiderivative, which we'll actually be spending lots of units on in the future. So we need to figure out what term would give us this as its derivative. We already know that this exponent would have to be increased by 1, right? It's going to be t squared. But this constant part, right? Remember, when we're doing our derivative, this exponent would be brought down and then multiplied by what's there. So 2 times what is going to give us -4? Well, we need a -2 right there. And then to get a constant like this, we need a linear term, right? So it's going to be 3t. And when we take the derivative of that particular term there, we get 3. So going from our position function to our velocity function involves taking the derivative. That's something that we are well acquainted with at this point, this process of finding a derivative. And what we kind of did here has another name. It's called the antiderivative, and I think it makes sense why we would call it that. It's sort of like taking the derivative in reverse. Derivative. Struggled with that word there. There's one other component here that the antiderivative has to it. I missed out when I didn't write it down. That there could also be an addition of a constant on this position function, because when we look at this position function and we take its derivative, the derivative of a constant term like that is 0, right? And it goes away. So anytime we're actually taking the antiderivative, we'll always have to consider this constant that's there. It's not really for us right now, but something to keep in the back of your minds. Alrighty, now here's a few things that I'd like to go ahead and point out about what we did today. So first of all, it's this relationship between position, velocity, and acceleration, right? Position function, we used s of t. That's a somewhat common notation, but we may see some other things like that. The derivative of our position function is equal to the velocity function, right? Because a change in position is velocity. And velocity, it's important to remember that it's not just speed. It's not exactly the same thing as speed. It's also a direction, right? We tend to have a positive direction and a negative direction. We need to pay careful attention to that. And then we have the second derivative of our position function, or the derivative of our velocity function, which is acceleration, right? The change in velocity is acceleration, which you may remember from your physics class. All right. Second thing we have here are a couple important things to remember about velocity. When your velocity is equal to 0, that means the object's at rest. It's not moving, right? There's no change in its position. When the velocity function is greater than 0 is a way for us to say positive. So when the velocity is positive, the object is moving right or up. It's getting bigger in the positive direction. And when the velocity is less than 0, it's another way for us to say negative. So when the velocity is negative, the object is moving left or down, or moving in whatever direction we indicate as being negative. All right, now finally, we have this nice chart here to sort of help us out with the relationship between velocity and acceleration, which can be sort of tricky. It kind of goes along with this speed having a direction, right? So when our velocity is positive and our acceleration is positive, we're speeding up, right? Because our velocity is changing to be even greater in that positive direction, so we're speeding up. And that's the same thing over here, right? In both these cases, we notice that it says speeding up because our velocity is positive, our acceleration is positive. Whereas here, our velocity is negative, it's less than 0, and our acceleration is negative. So we're already moving in the negative direction and getting more negative, or accelerating in the negative direction also. Whereas when those two things are working against one another, when our velocity is positive but our acceleration is negative, slowing down, or when our velocity is negative and our acceleration is positive, also slowing down. So you have to kind of pay attention to the sign of each of those things, right? Compare the sign of the velocity and acceleration. If they're the same, we're speeding up. If they're different than one another, if one's positive and one's negative, that's going to indicate that it's slowing down. Anyway, try those check your understanding questions, and I'll see you guys next time.